Okay, so hi everyone. Unfortunately, the physical lecture was not recorded, or rather, there is an audio but no video. So I'm going to redo it now. So last time, in the missing lecture, what we covered is the Saks-Zhou algorithm. We continued to describe the Saks-Zhou algorithm and analyze it. And also, we started to talk about a little bit about randomness extractors and proved, gave the construction of mergers by Zev Dvir, a celebrated construction, which is, it's really beautiful and it's related to the problem of Kakeya sets over finite fields. So we'll do both here, starting with Saks-Zhou. So Saks-Zhou's algorithm, it's really a magnificent algorithm in pseudo-randomness, dating back to 94, 97, depending if you're looking at conference or journal version, is an algorithm that essentially takes the power of a matrix or the product of matrices, but let's keep it simple and work with powers of a matrix. So as its input, it gets a matrix A, so that's going to be a stochastic matrix. It also gets a number n, that's the power you want to raise a to. And what you want to output is a to the n. And as usual with space, it's, usually you kind of want to make it explicit that you want kind of local information. So the input on top of a and n is also indices I and j. So these are coming from the dimension of A. So A is going to be a W by W stochastic matrix. I and J are the entries you want to get from the nth power of the matrix, right? And, technically, up to some explicitness, you are also given a number t, and every entry in A is represented using t bits. So t bits of accuracy in every entry of A. And so Saks-Zhou doesn't do quite that. It also given yet another parameter epsilon, which is going to be the error, and the output should be this plus minus epsilon. So you are allowed to approximate rather than actually completely accurately compute the nth power of the matrix, and you want to do that in a small space. And you can actually just try to do that by yourself. And if you just do that, kind of do essentially the first idea that will come to your mind, I guess, is you're going to take repeated squaring, truncating the intermediate results so that you won't get too much space, and work it out. You'll probably get something like, so this is Saks-Zhou, and this is you, most likely. Maybe you are Saks-Zhou. But if you're going to try and do that, and that's all, by the way, problem 6 in the homework, you're probably going to get something like maybe definitely something which is polynomial in log n, log w, log 1 over epsilon. And if you're looking at the dependence on t, it's always you're going to have some t there. And if you're not too careful, you're going to get something like this squared times log n or something like that. But you can be a bit more careful and get such a result. Everything is O, of course, O notation and hiding constants. So this is the space complexity that you'll probably get if you try to do that kind of naively, or less naively, but not not paper worthy. So and indeed, actually, using Nissan, you can get this space complexity. And let me just remind you of that, because we kind of mentioned that to some extent in the previous lecture. So let me erase what you're going to do, because it was just for fun. So Nissan, Nissan is a PRG. It's not an algorithm, but you can use it as an algorithm in particular. So Nissan, what is Nissan's PRG? Let's remind ourselves. So this is this function which will just denote by PRG here, and you get a seed, or let's actually be more. You get a seed, and the seed is going to be J hash functions. H is a family of hash functions from, let's say, sigma to sigma, a set we just call sigma to sigma, and it's pairwise independent. Okay, so the PRG takes this, it takes an element from sigma, and it produces 2 to the j symbols, a sequence of 2 to the j, of length 2 to the j over sigma. And the guarantee of this PRG, it has also like these two parameters, epsilon and delta, right? Which stands for, doesn't stand for, but they relate to the accuracy and the confidence. This we did last time, so I'm just recapping it here. So what we proved about this Nissan's PRG is that for any width W, length N, well, length 2 to the J here, read one's branching program over alphabet sigma, right? So it looks like you have like W states, every layer, you have N layers or N plus 1, depending how you count those. And the number of edges going out of every state is, the set of edges going out, the labels are exactly sigma. Right, so N is, sorry, I'm kind of confusing N with 2 to the J. So N is going to be 2 to the J at the end, but the way you construct this thing is using recursion, so I'm kind of keeping J alive. But at the end of the day, J is going to be log N. And this PRG fools these kind of computations. And by computations, I mean that if you designate, if this graph induces a computation, a function, in that if you choose a start and an accept state, the first and last layers, and so an n bits, or sorry, an string of length n over sigma is going to be accepted, going to be 1, right? You get 1. By this program, if exactly when you start from the start state and you follow the symbols, you get to the accept state. Good. So this PRG has this property that not only that with expectation, the expectation over the entire seed approximates the right probability of arriving from the start to the accept state, but rather you get a stronger notion, which is, for any read once branching program like that, for all, let me just use my except with probability delta over this vector of hash functions, we get that the expected value of, so you take the expectation over the remaining of the seed, this part, and you look at, whether or not you got using this sequence that the PRG generates, given X and H, the way it's written, it's H and X, never mind, is roughly the probability. It's roughly, let's call it the expectation of P over uniform. Right, so not only that, maybe I should say put epsilon here. So not only that, when you take the expectation over the seeds, you get something that approximates what you want to approximate, but rather there is some stronger notion here that for every read once Bungie program, except with this confidence probability delta, and this is taken over the hash functions of Nissan's, then when you only average over X, this one symbol X, uniform symbol, namely, H is fixed, and you go over all X's. For every such X, this is an N sequence of length N over sigma to the N. We call it an instruction. So when you use this instruction to, start working from the accept state to the last layer, then the amount of times, the fraction of times you're going to get to the accept state is roughly up to epsilon, the parameter here. The accuracy parameter is the probability of actually accepting, getting from the start to the accept state under the uniform distribution of sigma to the N. Okay. And what more we said about this? Well, we said that, for any epsilon delta that you want, every hash function, so the size of H, or maybe the log the size of H, is going to be a log n W over epsilon delta. We proved that such family of hash functions suffices using the expander mixing lemma. And here I'm kind of assuming, therefore, that the alphabet, the arity sigma, is at least that. Okay. If you have a read-once bunching program with lower arity, for example, arity 2, then you can always simulate it using larger arity. And here I'm just going to assume that it's large enough to begin with, avoiding this middle step. And this means everything is O, of course. And this means that the seed length, right? You have J of those. So, let me call. Okay, you have J log n W over epsilon delta if you want to full read-once bunching program of length J, but J is log n. So at the end of the day, as I said, J is log n. So the seed length of Nissan is log n times log n W over epsilon delta. So it's a randomized algorithm, but it has this. It's a PRG, and but you can think of it as like, many PRGs. For every given H, you have many PRGs, one for every H, and that PRG has a very short seed length, only sigma, only this. It doesn't suffer the log n multiplicative factor that you get at the end. Another thing we said is that, given H, the space complexity for computing Nissan is also that. And the reason is that, if let's do proof by picture, if you draw the recursive tree, right? So maybe, this layer you have H3, here you have H2, and here you have H1. So here you are going to output X according to this recursive tree. You are going to output X. Here you are going to output H1 of X. And here you are going to output H2 of X, because, the reason you output H1 of X here is because you have an H1 sitting here, which acts on what it gets from the left. And here also you get X, and then you get H2 of X, which goes here. And then here you're going to have H1 of H2 of X, and so forth. And the point is that any index that you would like to have from this PRG, right? This PRG output element in sigma to the n. So for every I in n, you're going to ask this PRG, what's the I symbol that you're outputting? Then according to the Brit representation of I, every I is really a leaf in this recursive tree. So according to its bit representation, whether you go left or right. When you go left, you don't apply the corresponding H. When you go right, you do apply the corresponding H. So you're going to have a J or log n at the end. Log n levels here at when you go over all the bits of this I. And for each of them, because H is already written in the input tape, you can evaluate on the existing value, the current value, you can evaluate or not evaluate, depending on the bit, the corresponding H. That you can do in this space, okay? Because our H's are, as we did in one of the earliest lectures, I think, is of the form AX plus B for some A and B that determines H, and and so forth. It's something you should verify and know or read about, but you can do arithmetic in log space, at least in that case, where the field is of characteristic 2. Definitely in that case. Then and you have log n of those, but you always reuse space, right? So you computed the current value and save it somewhere. It's of that number of bits required to store it, and then you can apply the next stage or not, and the next stage or not, and so forth. So you can do everything here in space, which is this thing. So the ith output of the PRG can be computed in great space. So from here on, let's denote this by G for great or good. So what you want to take from this part, this recap on Nissan, is that, okay, so its seed length is not great. It's G times log n. This is G. But when you fixed H, namely the sequence of hash functions, and you think of them not as kind of randomness, but rather as an input that you can read again and again, that's one way to think about it. Then the space complexity for computing every output symbol of the PRG is G. And also this expectation is taken over only G things, right? Or 2 to the G things. Like this is the sample space size. Good, so that's just a recap on Nissan. And how can you get an algorithm for taking the power of a matrix using Nissan? Well, the idea, as we said last time, is just to, Nissan works with branching programs. It doesn't work with matrices. But there is an obvious relation because usually it's obvious in the different direction. If you have a graph, then you have the corresponding adjacency or random walk matrix associated with it. And here we are going to do the other way around. So given a matrix, we are going to come up in a kind of canonical way, a branching program, read-once branching program, or that allows us to, take that corresponds to the nth power of the original matrix. So for example, if you have this matrix A, which is, I don't know, say 1/4, 3/4, so it's stochastic, half-half. So T here is 2. You need 2 bits to represent the entries because of the 1/4. So the corresponding graph for this matrix is going to be, it's going to have the same width as the matrix, so 2 by 2 here as well. It's going to have like length 1. And what you're going to do, you're just going to, put the right fraction of edges between the vertices, right? I need to kind of spread 4 edges here from that vertex to these two, and I just spread them in a way that respects this ratio, right? And same for the next one. So I put 2 here, say, and just put in 2 and 2 here. And the point here also is that T, the number of bit of accuracy, translate exactly to sigma, or more precisely, sigma is going to be 2 to the T, right? Because this is the kind of granularity that you are working with. You need that number of edges to maintain it without loss of inaccuracy. Okay. So if you want to consider a to the n, then a to the n will just, you can just take this branching program, this like length 1 branching program, and make n copies of it. And then clearly that a to the n ij is going to be, if this is the ith vertex and this is the jth vertex, then it's going to be the probability of arriving from here to here if you take a uniform sequence of symbols. Okay. So, what Nissan tells you is that not only there is a way of doing that, but and also you can do it I'm not going to go over that, but this kind of reduction from matrices to branching program is space efficient, right? In the sense that if you ask for a given node and a given edge, like an element in sigma, who is my neighbor, then you can do it in log space. But never mind that. I mean, it's important, but never mind that. it's just technicality. So the point is that using this little observation or like adapter between branching programs and which Nissan likes and matrices which we are focusing on, what you can do is you can just get this following algorithm. So we are going to call it Nissan. So this algorithm is given two parameters, epsilon and delta, and let's call them epsilon Nissan and delta Nissan so that we won't confuse them with the epsilon and delta of the final algorithm. So Nissan is an algorithm. So as an algorithm, but it's a weird algorithm. And so an algorithm, it gets the matrix A, again, stochastic and so forth. It gets N, and it gets, so I should say it also gets I and J, but we kind of suppress it usually. Never mind. And that's the weird thing, it also gets H. So sorry, this H is the sequence of hash functions from before. So this H lives in H to the log N. So there is some confusion here. This was 2 to the j before, let's call it just n, and I and j are just the entries. This is not the j, which is the log of that. And also just because I don't want to really carry it through, let's remove the I and j. We always access things in this fashion. Okay, so this algorithm gets A, N, and H. H is not going to be random here at this point. It's just this thing, just an input. And what it does, it translates, so it's going to output, it's going to approximate A to the N up to plus minus epsilon Nissan with high probability, namely, except with, let me just write it like that, except with probability delta H over H. Now, it's not, the point is that, this algorithm as an algorithm is not a great algorithm because you give him H as an input, and for some H's, it's not going to work, okay? But I want to think of H as an input to the algorithm because this algorithm is going to read it more than once. And it's just more instructive to think of it like that as an input. So this algorithm gets A, N, and H, and it's going to output an approximation of A to the N up to plus minus epsilon N. And it's going to be correct for most of the inputs that you're going to give it as a third argument. For every A, there's going to be different H's that will work, but many of them will. And the way it works is really simple. Like it's going to produce from this A the branching program P in the way I described here. And you should maybe want to verify that you can do it in log space. And then what you're going to output is, so you're going to output the expectation over X in sigma. Right now, sigma is, as I said, is 2 to the number of bits. Right, the sigma of the branching program is the 2 to the accuracy in terms of bits of the entries of the matrix of, P applied to Nissan's PRG with H and X. And I'm just going to not write this arrow anymore. This is going to be the last time. Okay, so what's this algorithm? Well, indeed, I mean, just by looking at it, you can see that it does what I'm saying it does because that's the promise that we inherit from the PRG. And the space complexity, so it's a deterministic algorithm, right? The space complex, so I don't have to analyze randomness, but the space complexity is, well, if you trust me that this is not the bottleneck, then this is going to be the bottleneck, which is going to be the same, and it's going to be what we call G, or order of G, namely order of log n W over epsilon Nissan delta Nissan. And from that, if you want to get a final way, so I need this. I'm going to need this component, this kind of algorithm, okay. But if you want to branch out to cache from this immediately, then you can immediately get a space. You immediately get a space G log n algorithm for approximating, a to the n. And the reason is that, this thing works for most h's, right? So what you're going to do is you're going to go over all possible h's. Every h is of length g times log n, right? Because every hash function in the sequence is of length g, and you have log n of those. So you just keep track, right? You go over all possible h's. You need like you have this vector of h's here, which is composed of h1, h2, all the way up to h log n. You have g log n bits here that you just iterate over, and for each fixed sequence like that, you're going to compute this. So the fact that the PRG is efficient, it runs in space G, and the fact that you can, looking at the matrix A, you can immediately kind of understand, given the if output of that, where is the state I should move to from my existing state, and the fact that the expectation you can do with just an additional log sigma bits, all of that tells you that you can compute this in this space. And you just kind of reuse the computation for different h's for when you compute this PRG, and you also need to keep a counter, right? So this is a counter which tell you, you're just going to take the average. So for every h you're going to get a number, you're going to add them up. So you're going to need these many bits because the number is going to grow. And yeah, and then and then you're going to take the average, and that's going to be the answer. You can also, by the way, take the median, but it's slightly more tricky to do median in log space. You can try to think about that. Right, because most of them will work, right? So if you have these h's, say this is the right value. Say this is the right value, then for most h's you will get close up to epsilon Nissan, you'll get close to the right value, and only delta fact, only a few of them will miss. So median will work in a sense even better, because the confidence won't mix up with the accuracy. Okay. So that gives you an algorithm that runs in space, a deterministic algorithm that runs in this space for approximating a to the n, where I'm ignoring the error. So for constant error. For non-constant error, you get it somewhere here, I think. But for constant error. Good. So what Saks-Zhou did, so their algorithm shaves the square root of log n factor. So instead of space log n times log n w, which you get from Nissan, or if you do the homework very carefully, they got square root of log n times log n w. One more square root, and we're very happy. By the way, in a recent work, we and also kind of concurrently, independently, two students from Harvard, Pine and Puterman, they managed to improve that, and we managed to improve that to log n plus square root of log n log w. So we got the square root log n. We got the dependency in n correctly, which means that if the matrix if w is not larger than like 2 to the square root log n, you get essentially optimal result. And there's also a result by William Hosa that shaved a log or maybe polylog log n factor from this result, from the Saks-Zhou result. Okay. So how does this work? So we actually said all that, but let me just repeat it. So the idea is to say, let's be a bit more aggressive in terms of power rings because, okay, so instead of taking a and square it all the time for log n steps or recursive depth log n, what we are going to do is we are going to take higher powers. Let's call it 2 to the r1. So r1 is not 1 anymore. And that we'll need to do like log n over r1 times, if you think about it for a second, which we are going to denote by r2. And if you just try to do that, you gain absolutely nothing. So, I mean, the way you do this thing, the way Nissan works, really, it uses an h, right? It uses some h here in order to approximate a squared. And then it uses another h to approximate the square of the approximation, and so forth. This requires you to have log n h's, and each h is of length g, like it's a good length. And that's why the seed length is g times log n, because you have log n hash functions, each of length g. Again, g is log n w. G is good, it's the log of everything. And here the idea is you say, well, you know, if there is this kind of imbalance a little bit, or not a little bit, there is imbalance between the space of computing that and the length of h and so forth, maybe we can benefit from doing it with like increases the length of the h1s and have less h's. Right here you have only r2 h's, and each hi, h1, h2, and so forth, is not going to be g anymore. It's going to be something that depends in r1. It's going to be essentially r1 times g. But it just doesn't help you, right? Because if the length of if the length of all the h's is, you know, if the length of a new hi, every hi, is r1 times g, and you need r2 of those, then you get again g log n. Nothing happens because r1 times 2 is g. In terms of seed length, nothing happens. And the point of Saks-Zhou was to say, well, and you could have done it here, but it wouldn't get you anything. The idea was to use the same h. Just reuse the same h all the time. Now, this doesn't make any sense because you can't have a randomized algorithm. You can just run your randomized algorithm where the input to the algorithm depends on the randomness that you are going to use. Right? You can't let the input move every time you move the randomness, because then, you know, for every input, there are some random bits that fail for it, and potentially it could be the case that someone managed to match for every input the bad randomness to it, right? If I know the randomness that you're using, I can potentially find that probably it's going to be hard, but find an instance that will fail for that randomness. Nonetheless, the idea was to use the same h, but between steps, in order to kind of make sure that this is over what computed using h is independent of h, typically, the idea is to kind of clean it up. So the idea is to take this matrix and to maybe use some more randomness for that process, but make sure that h is kind of obfuscated. You don't know, there is nothing about h here. I mean, looking at that, you will know nothing about h, and therefore you can reuse h again, again, again. And the key lemma, if you recall, little lemma about numbers and like little lemma about like facts of life, is that if you have two numbers, so say you have y and z, numbers in 0, 1, such that they're close. And let's be more specific about the exact parameters. Let's say that there are 2 to the minus 2t close. And so the drawing I have in my head is the following. So we have 0 and 1, and y and z are really close. And now what you're going to do is you're going to look at partitions of size 2 to the minus t, so significantly larger, 2 to the minus t of the 0, 1 interval. And what you're going to do is you're going to move these two numbers, y and z, I can do animation. You can move these two numbers in multiples of 2 to the minus t. And the game is that you don't want that to happen. You don't want y and z to sit in different buckets. You want them to sit in the same bucket. So the point is that if you move them, so potentially if you started to start with, it could have been that case that y and z sit differently. But if you're going to just move them a little bit, the probability that this event will happen compared to those events is significantly smaller, right? So formally, what you can do is the following. You can say that if I'm going to sample a number L, so that's the number of steps I'm moving y and z together. So the shift. So I'm shifting it by 1, 2, up to, maybe L is a bad name. L is going to be the length of L. So let's call it Z like that. So let's call it L. I mean, S is the best name, it's shift, but S is usually taken by other things. So let's do L for, as L bits, let's call it L. So if you're going to look at these two expressions, you're going to look at y, and then you're going to subtract from y L times minus t, right? So that means I'm moving y in this granularity of 2 to the minus t, and then I'm going to take I'm going to truncate it to t bits. So it's, of course, minus 2t. I want to keep the small granularity here. My bad. Right. And don't worry about it moving to the 0. It's actually going to be better if you go below 0. I'm defining it as 0. So you do this and compare it to the same thing, but you do it to z. Then what I'm saying is that this will usually be different. Right, so this means you shift y and also shift z by the same amount in granularity of 2 to the minus 2t, and you ask what's the probability that they will fall in the same kind of bucket here, because truncating to t bits exactly corresponds to falling in the same bucket, because the buckets start from 0 and are of length 2 to the minus t. Then that's going to be probably at most 2 to the minus l, assuming that l is at most t. Right, because you're not going to kind of do it a modulo again, right? So the proof is by picture. You are sitting here and you're moving it at most 2 to the minus t. So there is only like one. In this case, there are only like one bad event. This one. You don't do that. You do shifts to the right. So there is, this is bad. The rest are good. There is only one L that will be bad for you out of this. One capital L that's bad for you. So the probability for that to happen is at most 2 to the minus L. And then you can ask, what this has to do with anything. Well, the point is, you should think of y as what your algorithm produces. Output. I mean, our algorithm produces matrices, but assume your output, your matrix actually, your algorithm produced a number. It's going to be every entry in our matrix. Output of our algorithm. And this is actually the actual value. It has nothing to do with our algorithm. That's the right answer. So the point is that, the output of your algorithm, y, depends on the randomness that you used. And, typically it will be close to z, but it certainly depends on the randomness that you used. And in particular, it potentially can reveal some or all information about randomness that you used. And you don't want that. So what you're doing here is this lemma tells you that if you're going to invest some more randomness, L bits, but doing that, you can, if you're going to take the answer that you got, I mean, you don't know Z, but if you're going to take the answer that you got, shift it using L, and then truncate to T bits, so you're losing accuracy a little bit, then, with high probability, except with this probability, you're going to get the exact same value as if you would have done that to the right answer. So if you took the right answer, shifted it, and truncated it to t bits, I mean, that's not the right answer anymore, but it's something that you do to the right answer, something that you do to something that has nothing to do with the randomness that you used, and you're guaranteed to get, except with some small probability, that answer. In particular, since this all may depend on your randomness, but this is not, in the cases that you succeed, namely they're equal, then the thing that you're going to get is independent of the randomness that was used to produce it. Because it's just equal to something which has nothing to do with the randomness that you used. So that's the whole point. It's a way to kind of clear things, clear the randomness that was used, to get to where you got in order to compute this value of y. Okay. So in particular, or as a corollary of this lemma, you can replace this y and z with matrices and put a w squared here, by w matrices, and you will be guaranteed that the max norm. So every corresponding entry in the matrices will be the same, right? Rather than just numbers. So with this lemma in mind, and with Nissan's algorithm in mind, we are ready to actually state the Saks-Zhou algorithm. And I'm going to do again the following. I'm going to assume, because I just want to break it into 2 steps to make it simpler. So of course you are given A, you are given N, but again, let's assume we are given H. Okay? So again, this is not quite a randomized algorithm, it's a deterministic algorithm, but it gets H as input, and H has this flavor of being random, usually. And what's H? So let's talk about that. So H is what you think is a sequence of hash functions, but of length R1, just enough to get the matrix to the power 2R1. So let's have a bank of parameters. So the main parameter is going to be T. We'll talk about that. There's going to be L, which we'll talk about. I mean, L is going to be this thing that we just did, the number of bits you invest in order to shift things. And we're going to, I mean, it's at most T, and we need it to be close to T, so let's take it to be T over 2. We are going to have, so R, which is just a shorthand for log n, is going to be R1 times R2. And we are going to need to figure out what R1 and R2 are. They're going to be square root of log n, but you'll see. And there are also, there are also 2 other parameters, epsilon, Nissan, and delta Nissan, which we'll talk about. And I think that's it. So the idea of Saks-Zhou, and I think I was incorrect. Saks-Zhou is going to be a randomized algorithm, not a deterministic one. But H is not its randomness. H is part of the input. Okay? So what we are going to do is, that's the input, the output is obvious. I mean, you want to approximate A to the N, plus minus something. It's not epsilon Nissan, it's some other epsilon, which we'll talk about. It's of course related to these parameters. Surprisingly, it's not related to epsilon Nissan, it's related to T and so forth, but we'll see. And the algorithm is as follows. So H is going to be a sequence of R1 hash functions. And the algorithm is as follows. So for some reason, I prefer to move to M's rather than A's now. So we're going to set M0 to be A, or maybe M0 tilde to be A. And then I'm going to do what I'm writing as a 4, but technically it's not a 4. So I'm going to have R2 iterations. In these iterations, I'm going to take the next power. So I'm going to use Nissan with parameters epsilon and delta on A minus 1 tilde with H, same H, there is no HI, same H all the time as promised. Okay. and I need some parameters. I mean, we all know what are the parameters. So I'm going to use this h to approximate this matrix to this power. Okay. Now that's not going to be my mi plus or mi tilde, because it does depend on h. So let's call it ni for Nissan. And then we are going to compute mi tilde, finally, by doing the process that I told you to this ni matrix. So we are going to take ni, and we are going to subtract 2 to the minus 2t times this li times, let's talk about li in a second, times j. So j is the all ones matrix, just doing the same. I'm doing the same shift for all with the same li to all entries of the matrix, and I'm going to truncate to t bits. These li's are actually is the randomness of the Saks-Zhou algorithm. So that is a randomized algorithm. So it has, let me just, so it has randomness z1 up to zr2, right? You need r2 of those. We don't reuse shifts. They're going to be cheap, so it's fine. And each zi is of length L, right? Little l. So we need LR2 random bits here. But anyhow, at the end of the day, what you are going to output after the 4, we are going to output MR2 tilde. So that's the entire algorithm. But for the fact that it's, first of all, it's still randomized. It's not the end, like the final algorithm. It's like the important component. So it's a randomized algorithms in terms of it gets the zi's, but it's also getting this h, which I think of it as an input to this algorithm. And look, I'm using the same h again and again, right? So I'm using h, get a matrix, which certainly depends on h. Then I am doing something which hopefully will decouple this matrix from h, and then I'm reusing h again, and so forth. So in pictures, the picture you should have in mind is the following. You start with A, which is M0 tilde, and then you do like a Nissan step. So that depends on H, right? It approximates, it tries to approximate M0 tilde to the 2R1, but it does that using H. But when you do this shift and truncate step, so that's a good step. Let's do it in green. Shift and truncate, which gives you M1 tilde. And here use Z1. Use the first L bits that you have in your SID to do that. And then you continue like that. You do another Nissan call. It again depends on H. You get something which is close to, well, technically to M1 tilde of 2R1, which hopefully is close to M0 tilde, like A, of 2 to the 2R1. And then you do another shift and truncate. Now with Z2. Okay? And we want to analyze that. We want to kind of, essentially at the end of the day, what you want to do is to compare this, or, if you had an I here or R2 here at the end, to the corresponding power of A, right? But the point is that, even without these H's, it's not the right thing to do. I mean, because you do these shifts and truncates, even without relation to Nissan at all, if you just do the shift and truncates every time, so you take a 2 to the R first power, shift and truncate, using the randomness that you use here. And then you do another, I meant L. And then you do another shift and truncate, and I have a recollection that it's here as well. Yeah, I meant L, sorry. I'm used to Z's. You do another shift and truncate. So these matrices are not quite going to be A to the N, and they are closer to the matrices that we're actually doing. So what we are going to do for the analysis is to look at the matrices that are obtained like just in the analysis by doing the shift and truncate without Nissan. So what am I saying? So let's define so we're going to find a sequence. We're going to call them MIs without the tildes. So MI is going to be, you take the previous element in the sequence rather than Nissans apply to it. And then you're going to do the shift like we did here. I'm just going to replace this Ni with this. So the actual power, not an approximation of that. But I'm going to define that recursively, and M0 is A. So that's another sequence of matrices, which is, it's not, at the end of the day, it's not going to be the right power. So MR2 is not going to be exactly A to the N, but it's going to be a good approximation for that, we'll see. And it's closer to what we're actually doing, right? The only difference is this. We don't do this middle step. In particular, this sequence of matrices depends on the LIs, but not on H, right? So if I want to draw it here, So here we have, this equals also M0, and here we have M1. No, sorry. Here we are, the corresponding thing here is to look at M0 to the 2R1, no HS, and then do the shift and truncate to get M1. Right? M1 is obtained by doing the same process you did to this matrix. Right? What you did to this matrix to get here, you do the same to that matrix to get to here. And then you have, another one. Let's maybe move this a little bit. You have another one. You take this matrix to the 2 to the R first power, and then you do again shift and truncate using L2. Right? And the main part of the proof, let me just sketch it because we kind of did it last time. The main part of the proof is to prove by induction that if these are equal, then these are equal. And then therefore you get induction. Like again, with hyperbolic and so forth. So why is this the case? It's really kind of obvious, but let's do it. So, the hard part was actually to make sure you define what you need to define. So, think of it as I and I plus 1, but, it doesn't really matter. So say these two are equal, right? Then because they are equal, then this depends on H typically, but because they are equal, it's not depend on H, right? So whenever H is such that these are equal, H and the LIs are equal, then this thing that depends on H equal to something that does not depend on H, so it doesn't depend on H. So therefore you can apply Nissan. You can do this. It makes sense to apply Nissan to something which potentially looks kind of weird to look at because it depends on H, but it's not. So you do Nissan, and you get, and this thing is going to be try to approximate that, right? So to what extent? Well, again, except with some small probability and delta Nissan probability, this is going to be equal that. Right, I'm already kind of, yeah. And I want this to be 2 to the minus t close to that, so I can use this lemma about shifts and truncates here. I just kind of instantiated it with a 2 to the minus 2t. So I'm going to choose epsilon Nissan to be 2 to the minus 2t, because what do I know? I know that when this succeeds, namely when for Hs in which this is 2 to the minus t close to that, I know that the shift and truncate will make them equal, except with probability 2 to the minus L over the corresponding L. Right, so again, there are a couple of things here. So there are Hs and Lis which makes this equal, and there are Hs and Lis which unfortunately makes these quantities unequal. But for most, and you'll see how it evolves, but for most Hs and Lis up to that point, these are equal. Since they are equal, you can apply Nissan to this matrix because it's really that matrix, and which is independent of H, so it's fine. You don't give Nissan something that depends on H usually. So this is something that's independent of H now. You apply Nissan, and you try to approximate this thing, and it does, except with some extra probability over H that you lose, delta H. So typically, in losing another delta H in confidence, you know that these two are 2 to the minus 2t close, because that's how we chose epsilon Nissan. And once this happens, you know that because of the lemma about shift and truncate, you know that except the probability 2 to the minus L over the corresponding L, these are equal. And that should just proceed by induction. So if you think about it for a second, what you can infer from this is that the probability that mi for any I does not equal mi tilde probability over H and the L's, okay? The vector of L's is at most, well, so if you think about it, every time you add to the previous confidence loss something, so it's going to be I times, because you do it I times, and the things you lose are, so now they are equal, so everything's good, it's independent of H. The first thing you lose is Nissan, right? Nissan loses delta Nissan of confidence. So for most H's, but for delta H, you know that this is close to that. So you're going to lose a delta H, delta Nissan because of the H. And then, assuming these are fine, you're going to lose W squared 2 to the minus L here, because the shift in truncate has a confidence which is W squared 2 to the minus L, right? Good. So in particular, at the end of the day, that actually we proved last time, but it's really follows from the picture. So at the end of the day, the probability that MR2, which is what we care about, fails to equal, or I should say that, M tilde R2 fails to equal MR2 is at most R2 times that, and in particular is at most, okay, let's keep it like that. Good. So kind of that's it. I mean, what we just showed is that this sequence of matrices that we compute equals, not no approximation at all, to another sequence, except with some loss in confidence. And the next thing we need to do, but it's kind of smaller, is that that other sequence that we just have in the analysis, not in the algorithm, but turns out that it's actually what we get in the algorithm with a probability, approximates well a to the n. I mean, the last matrix there should approximate, this matrix should approximate a to the n. But the point is that, once this is small enough, like if you are shooting for confidence parameter delta, if you take your delta to equal to this bound, or smaller than that, then this sequence of matrices will match that, and then the accuracy is going to be, it's kind of going to have nothing to do with what it did so far. It's going to have to do with to what extent are these shift and truncate hurt the accuracy. Okay, so if we are looking at that, by the way, just maybe before proceeding, you see that it gives us some requirements. So let's say I'm shooting for a final delta which is constant. Okay, I don't mind, like order of 1. I don't want to also carry this little delta. So you see from here that we need to choose R2 to be or delta n to be at most like 1 over R2, and R2 is at most log n. So trust me that it won't matter, and I'm just going to take delta n to be log n, 1 over log n. I could have chosen 1 over R2, of course, up to some O's. And the second thing is that, more important thing a little bit, is that we need this to be smaller than 1 as well. So L must be at least like log W or 2 log W plus log R2. R2 is log n, so really L needs to be, because of this constraint, we need to take L to be at least 2 log W plus log N. So L, and therefore T, so let's do it with T, needs to be at least, everything here is at least yet, at least log W, again, I'm ignoring the constants, plus log N. This is my way of writing log N. And in a second, you will see that for another reason, this would be replaced by a log N. So that's going to go away in a second, but let's keep it. Good. So the second thing we have to do is to ask, how close is mi to a to the corresponding matrix power? And if you think about it, it's this matrix that you care about. It's a to the 2 to the I R1, right? So that when I equals R2, you get here log n, which gives you a to the n at the end. So the thing you can prove, I mean, that's not so hard, but let's just do it. You can prove it for every matrix norm, but let's do it for the infinity norm. I like it for two reasons. It's an induced norm, which means it's submultiplicative, and for stochastic matrices, it gives you 1. So it's going to be nice to work with that norm here, but it doesn't really matter. So what we are going to prove, we're going to bound it using kind of by induction, and the thing we are going to do is the following. So we know that mi is mi minus 1 to the 2r1, and when you do this shift, and truncate, right? So that's mi, and therefore it would be nice to kind of plug in this matrix in the middle. So to bound star, so star is at most, just by subadditivity of every norm, mi minus 1 to the 2r1 in infinity norm, plus mi minus 1 to the 2r1 minus a to the 2 to the I r1. Right? So this thing, because of that, what's the worst that can happen, right? So you have this matrix, and when you subtract from it at most, right? So you have this matrix, and then you subtract. So I'm looking at this compared to that. So I'm looking at what you did to that matrix to get this matrix. So you took that matrix and you subtracted from it, from every entry, 2 to the minus L, sorry, 2 to the L minus 2t. Right, at worst case, this is 2 to the L, but you do it in multiples of 2 to the minus 2t, and then you truncate it. And truncation can also hurt you by like 2 to the minus t. But anyhow, this is most like, up to being like pedantic, it's most 2 to the minus t. It's not, but minus t over 2 or something. So let's call it 2 to the minus t, even though you should be a bit careful and do that if you want, but you live once. So it's almost 2 to the minus t, entry-wise. So this means that this is at most w times 2 to the minus t, because it's the L infinity norm, right? So you don't even have a w square, not that it matters to anyone. This thing is you should be a bit more careful here. So what's going on here? So let's call it a double star. Yeah, it's also easy, but double star you can write as mi minus 1 to the 2r1 minus a to the 2 to the I minus 1 r1 to the 2r1. Right? That's kind of confusing because they're like 3 exponents, but the base one is really a matrix, so it's like that. And I mean, I don't know if you know, but let's denote by, maybe instead of star, let's denote it by epsilon I. Then this thing, I mean, if we didn't have this, then that would be epsilon I minus 1. Right? If you denote the I ferro like that. So the point is that I'm claiming that this is at most like 2 to the R1 times epsilon I minus 1. And the reason is that that's an easy claim, is that if you have a bunch of matrices, A1, AK, B1, BK, stochastic, and you know that the product of the AIs minus the product of the BIs in infinity norm is at most the sum of the individual errors. That's a little lemma that you can prove to yourself. It's very easy. For example, in the 2 case, and that's the general thing really, you're looking at something like that. And so what you do is you add and subtract, say, A1, B2. Right? And then, so add and subtract, so you can put it like that because of the subadditivity. And then because of the submultiplicativity of an infinity norm, you can pull out the A1 infinity norm outside, plus here also the B2. And this is at most 1. So this is 1 if it's stochastic matrix. And therefore you get 2. Like you get the sum of them, right? You get this plus that one, and you can, by induction, prove it in general. In our case, it's the same matrix even, so it's slightly easier, and you take 2 to the R1 copies of it, so that's why you get this 2 to the R1. This is the number of summands that you have. So all in all, what you got is that epsilon I evolves like 2 to the R1 epsilon I minus 1 plus 2 to the minus LW, I think we have there. Where is it? 2 to the minus TW. Yeah, it's the same thing, of course. So let's go 2 to the minus LW. And so if you think about it, this solves to 2 to the R1 of those. Right? Just essentially up to some constant. So this means that the accuracy parameter is only coming from here. So if you want this to be smaller than epsilon, your final accuracy parameter, and again, I think of it as constant for simplicity, then you will need a L to be like at least, but we'll take it with equality, log W plus R1, right? So our bank is full. So this log n is going to be smaller than R1 plus R1. We're not going to choose R1 that small. Okay, essentially plus log n, but don't worry about it. Good. So we are done. We know that with this setting of parameters, we get constant approximation with constant probability over the L's. Now let's wrap it up. So the randomness complexity of this thing, let's look at this for a second. Let's do the calculation. So the randomness is R2 times each Li is of length L or T. These are the same. And they're really log W plus R1. Right, L is of length log W plus R1. So it's, okay, so R2 times R1 is log n. Now this R2 times this R1 is log n, and you have this log W also, plus R2 log W. So this is the randomness complexity that you have. 1 second. Yeah. For some reason, I imagined something a bit different, but never mind. And no, that's good. Okay. So that's the randomness. And the length of H. Okay, and the space complexity of this thing. So what's the space complexity of this thing? So that's the point where I say it's not really a 4. You don't have a 4 when you do space complexity. It's a composition, right? I mean, when you come to compute mi tilde, you don't have mi minus 1 tilde available in tape for you because it's a big matrix. You don't have that. So what you do is you do a recursive call, really, not really a 4. And the rule of thumb here is if you have R2 recursive calls, then the space complexity is going to be the recursive depth times, there is some like meta things you need to take care of, but not the bottleneck, times the space complexity you need to do one iteration. And Nissan, we said, this is like smaller, and Nissan, we said, is going to have a great dependence in terms of space. So it's going to have this G. But in that G, n is actually, or log n is replaced with R1, right? Because you don't do Nissan all the way up to the n. So what's really going to happen here is like R1, which is the log n, but for that particular n, plus log W, plus log 1 over epsilon Nissan, plus log 1 over delta Nissan. Plus log 1 over epsilon Nissan and log 1 over delta Nissan are these. This is negligible. So you only care about that. You get a t here. Log of that is a t. Log 1 of that is a t. And t is log W plus R1. Okay, which is exactly what's written here. Anyhow, I mean, good. And you see, it's exactly the same as the randomness complexity because R1 times R2 is log n. And if you have a randomized algorithm whose randomness is the same as its space complexity, it's not really randomized. I mean, you can just copy the randomness to the space, to the working space, and do whatever you want with it. So in particular, you can average over. So what I'm saying is that you can immediately wrap this algorithm inside an algorithm in which it's not random anymore, and that is space complexity. And it outputs the right answer just up to some error. No like probabilities, just up to some error. Okay. And now the final Saks-Zhou algorithm will just, iterate over all possible h's, and for every h, it will compute the value, right, as we did before, as we wrapped up Nissan. Right, so the final algorithm, finally, we iterate over all h, and recall h is of length, we have like R1 times good, that's good, essentially. Say constant error, constant confidence. And in every such iteration, you apply the Saks-Zhou algorithm that we just had here. And that has space, I've lost it, and that has space which is R log n plus R2 log W. So overall space is, of course, you need that because of this, but then you have the inner, for every particular h, you require like log n plus, let me just make sure I'm not copying it correctly, log n plus R2 log W. Where is n? Okay. Okay, so this is negligible. And you have R1 plus R2 log W plus R1 log N. And if you want to minimize that, because the product of these two is log N, then you should take them equal. So eventually we indeed take R1 equals R2 equals square root log N and end up with final space complexity of square root log N log W coming from here plus square root log N coming from here, which is what we promised. Good. So, I know it was quick, but we already did 2 hours of that and 1 hour before, which was recorded. So the next thing I'm going to do is the Dvir's construction of mergers and, remind you a little bit about extractors, but, let's take a break.